So the second one. So proof by contradiction. So what is the meaning of to contradict means? To contradict from English perspective. To contradict means? From English point of view, what is the meaning of contradict? Next two. Vice versa. Okay. Okay, so this method is used. This method is used. This method is used so that this method is used to prove that a statement P say P of n and write P of n, or simply just write P. This method is used to show that a statement P is true by assuming to the contrary that the negation of P is true. I might be contradicting myself. So the key thing, you will be given a statement P, and then you are to confirm that P is true. So to confirm that P is true, we take the other way around, that the negation of that statement, or the way he said, the other side of the same statement is true. So e.g., show that there is no largest integer. Show that there is no largest integer. So to prove this, so let P be the statement there is no largest integer. So when we mean the meaning of negation of a statement simply means that you are denying the statement. So this implies, okay, so we use this, if P is a statement, then we use this sign to mean negation, or we use this sign, or we use this sign. This means negation of P. And to negate P simply means to deny P. So like if you say it is raining, then to deny you say it's not raining, for example. You say today is Tuesday, negation will be today is not Tuesday. So that's what you mean. So negation of P will be the statement so if in a statement there is no largest integer, then the other way around is to say there is largest, yeah. There is the largest integer. So if we are able to convince ourselves that the opposite or the negation of the original statement is not true, then we'll have confirmed that the original statement is true. So the key thing is now we need to show that the statement there is largest integer is not true or is false. So so we show that negation of P is false. I know if negation of P is false, then the P set must be true. So let there be the largest integer, say n. So we want to confirm that what we are saying in the negation of P is not true statement. So let there be a largest integer n. So we are assuming that there exists a largest integer whose value is n. Okay. So what is the two concepts? N plus 1. So if I claim that there is a largest n, we know that there must also exist another integer, n plus 1. Because when we add, if you have any arbitrary integer, and you add 1 to that integer, you must also get another integer. How do you know? Okay. If I give you 10, you know that if I add 1 to 10, I'll get 11, which is another integer. So this is absurd. Since n plus 1 is an integer, greater than n. How do we know that if you have an arbitrary integer n, when you add 1 to that n, you must also get another integer. So when you claim that n is the largest possible integer, then that claim is an absurdity or is not true, because when you add 1 to that n, you must get another integer. So therefore, the statement there is the largest integer is false. So therefore, by contradiction, the statement there is no largest integer is true. So in a nutshell, what we are doing is simply to show that you are given a statement to prove, and then you gave the other side of the statement, the negation of that statement. If you are able to show that the negation is false, then the original statement, so therefore the result false. So this was just a easiest or layman's way of proving by contradiction. But let's see another proof that number 2 show that root 2 is irrational. So prove that root 2 is an irrational number. How did they prove an irrational? This is an irrational number. What is an irrational number? Have you ever seen irrational since you came to this institution? When you are walking on the corridors, have you seen irrational somewhere? Or everything is rational? Okay, so recall, before we provide it, recall that a rational number is any number that can be expressed in the form A over B, such that this B is non-zero. Both A and B are integers. And usually when we say in the form A over B, mean that it can be written in the reduced form. So just to make that come out clearly, we say GCD of A and B is 1. That's to mean that a rational number is any number that can be written as a quotient of 2 integers, which can be written in the reduced form. Reduced form means there is no common factor except 1 for A and B. So like if I say 10 over 20 can be written in reduced form as a half. So to make that come out clearly, we should just say in the form A over B, B by common sense being denominator should not be 0. And then both A and B are integers. And GCD of these two numbers in this form is 1. This one. And an irrational number is a number which is not that. So the opposite of the negation of this is what defines an irrational. So an irrational, remember this is not part of the proof. We are just now recording what irrational is. So an irrational number is a number that is not. So, or you can rewrite all this, negate all these things. That a number that cannot be expressed in the form A over B, B0, these are integers and this is 1, or the reduced form A over B. So there's no common factor for A and B, apart from 1. So therefore now we can now provide the proof. So by contradiction, let root 2 be a rational number. So we are now moving away from what we have been given and now claiming that root 2 is rational. So remember, the negation of irrational is rational. So we want to claim that root 2 is rational, so that we are moving away from what we have been given to prove. So if we are moving away from what we have been given to prove, and we find ourselves hitting a wall, then we go back. And so then the original statement is true. So when now you say that, or we are assuming that root 2 is rational, then it must obey the definition of rational. So therefore, by that, this implies that root 2 can be written in the form A over B. Because by saying a number is rational, then it means that it can be written as fraction of two integers, reduced form. Then this means we can always remove. So 2 is A squared over B squared by just squaring both sides of this equation. And then I can always remove fraction by cross multiplying both sides by B squared, because from the definition of rational itself, these are non-zero numbers. So cross multiply, so which gives us A squared is 2 B squared. So A squared is 2 B squared. By the way, what kind of number is this? Remember, this and it. So what kind of number is 2B squared? What type of integer? Is even, okay? So we know that all even integers are of this form. Any number which can be written in the form 2n is an even number, where n is an integer. And any number which can be written as 2n plus 1 or 2n minus 1, this is odd. This is even. So that is an obvious result that you get to know. That for any integer n, if any number is written of the form 2n, then that number is even. If you say 2n plus 1 or 2n minus 1, then it's odd. So, and then what happens when you square an even number? Like if we square this, 2n squared, we get 4n squared. Is this still even? So because this is the same thing as writing 2 into 2n squared. So remember, n is an integer. So 2 times square of an integer is just another integer. So this is the same as 2k. So which is of the same form. Okay? So the square of an even number is also even. Then what is the square of an odd number? Square any odd number. Do you get even or odd? It's always odd, okay? Yeah. So then with that in mind, we can, what can we say about n? So a squared is 2b squared. So this is even. A squared is an even number, okay? So which means a is also even, okay? Because if you are getting that the square of a number is an even number, then the original number must have been even number. So this a squared is even, so is a. So a itself is an even number. So then now A is even. Actually, we can call this one equation 1. So B squared so when you say A is even, then we are saying that A can be written in the form. So A is even. What does it mean? So we are concluding that A is even because the square is even. Okay. So since A is even, then A is nothing but 2K, where K is any integer. That statement is by the definition of even. But if you say A is even, then it can be written as 2 times. So then now substituting, so maybe call this one 2. Substitute 2 in 1 to get. So where there's A, I'll put 2K. I'll have 2K. But remember, here is a square. So squared equals to 2B squared. Then this, so 2B squared will be 4K squared. So 4K squared. And you can make B squared. So which implies B squared is 2A squared. What does it tell you about this? Okay. Okay, what does it tell you about this? Is even, okay? Because B squared is written as 2 times another integer. Remember, K squared is just another integer. So this is B squared is even, so is B. So then now this means that B can be written as say 2n. Other thing that so it can be written as 2 times another integer. So this n is another integer. Then B is 2n, A is 2k. So where we came from 2 times A over B. So the written as A is 2k and B is 2n. So is a GCD of A and B 1? Is a GCD of A and B 1? So this implies that GCD of A and B is 2, which is not 1. In fact, to make this statement more clear, we can say, after showing that B is also even, then we say this is an absurdity since GCD of A and B is 2, which is not equals to 1, as per the definition of rational. So therefore, the number root 2 is not rational. And when you say root 2 is not rational, then it must be rational because that's the opposite. So the definition of a rational number, take into consideration when you say a number that can be written in the form A over B, we mean A and B are in the reduced form. Reduced form means GCD of A and B is 1. So that's why we're saying that by doing this, A is even, so multiple of 2, B is even, multiple of 2. So when you give it divided, then these are 2 even numbers. And 2 even numbers, the GCD is 2. The possible GCD is factors 2, which is not 1. So that is an alternative condition of rational. Requires this to be used. So more other proposals, we'll discuss them now based on the problems that we'll be solving in the next problem session. The key proofs which actually are very obvious in terms of selecting problems directly as the principle of mathematical induction proved by contradiction. So we'll supply more problems to help you see how we do proofs. We also have what we call direct and other methods. Yeah. So I'll there for this. So from here, got it.